end behavior of rational function, you're going to examine the corresponding quotient of the leading terms. So there are two cases for you, okay? Case 1 and case 2. We're going to talk about case 1 first. Case 1, we talk about horizontal asymptote. Now, there are two types of horizontal asymptote, okay? The first one is when you're going to get a number. So y equals to a value. The second one, you're going to have y equal to 0 and only 0. So to find the first case, which is the horizontal asymptote, you're going to look at the quotient of the leading terms. And that quotient have to be a number, which is a constant. Okay? That constant, bless you, will indicate the location of the horizontal asymptote. So each of the wording there is important. Let's go over an example so you can see. So here is a rational function. So you can see that you have a polynomial on top and a polynomial on the bottom. Hi, go ahead and put your phone in. So if I'm looking at this rational function, what I want to do is I want to look at the leading term. Remember, the leading term does not mean that it's the first term that you see. The leading term is the term with the highest exponent. Are we good? So when you look at this, you're going to see that the highest exponent is a 3. So in this case, my leading term is 2x to the third. That's the leading term on the numerator. On the denominator, which is the bottom, the leading term is also x to the third, because that's the highest exponent for all three terms when you compare them. So what I do is I take the leading terms and I divide it. That's what quotient means. You divide. Now, if you notice, you can see that x cubed cancels out with x cubed. So you're going to get a 2 once you simplify. That 2 is the constant. And this constant represents your horizontal asymptote. So in this case, for this function, the horizontal asymptote is y equal to 2. Is that good? Now, Ms. Tran, what the heck does that mean? It means that your function, as it goes to infinity, it will flatten out and it will approach 2. It will no longer go up to infinity or go down to negative infinity. Are we good? So we're going to write that so you understand what the heck this means, okay? It means that the limit as x approach infinity of this function, we're going to call that function k of x. Your limit, your function, your y, is approaching 2. That's what this means. Okay? So for example, I think I can graph this out and you can see, yeah? So we're going to graph this out, and that way hopefully you can see what I'm talking about. Okay, let me graph this out so you can see it, okay? And this one is x to the third minus x squared plus 5. So now if I were to graph this, all right, now if you take a look at your graph right here, let's pay attention please. You're going to see that as x goes to infinity, you guys see that your function sort of flat out. Do you guys see that? And the same thing as x goes to negative infinity. So now what I want to do is I want to take a look at where this one goes. So I'm just going to trace that. And you're going to see that, notice, look at your y. As x goes to infinity, do you guys see that your y is approaching that 2 right there? Oh. You guys see that? It's approaching that 2. You see it? So that's what we mean when we say look at the horizontal asymptote, because your graph is going to go in that direction. let me go back. So if you look at this one right here, this is the left end. So if I move on the left, take a look at your y, okay? Look at your y. So as x get bigger and bigger on the negative value, or more and more negative, you're going to see that your function is approaching that 1.9, that 2 mark. Do you guys see that? That's what we're talking about. So here, when we look at limits, and you have a horizontal asymptote, that means as x go to infinity, your function is approaching a single number. Is that good? Question on that. Now notice, for this function, not only as x approach infinity, the function approaches 2, but it's also the same on the left end. So as x approach negative infinity, your function is also approaching 2. So that's what that means. Shh. Question on that. Can we move on? This, you got to make sure you're clear on this, because as I ask you for these things, you got to know how to find it. Okay? On the AP exam, they might give you the answer. They're going to say the horizontal asymptote is 2. Which functions gives you that horizontal asymptote? Did you guys see that? So they're going to ask you to go backward. How? You're going to look at the leading term of your multiple choice answer and see which leading terms, when you divide, give you that value. That's how you do it. The other case is where you have a horizontal asymptote y equal to 0. That is when you take, again, the quotient of the leading terms, yeah? And you're going to get a 0. And this is how you get a 0. It says that the degree of the numerator is less than the degree of the denominator. Okay? So for example, I'm going to call this x sub n, n for the numerator. And then this is x to the d power. So the d is the denominator. We're going to call that, yeah? So when you have a horizontal asymptote of 0, the numerator degree, this degree, n, is going to be less than the denominator degree. Okay? So that's what this means. Now, we have an example just so you understand why that's happened. So here's an example. I have a rational function x squared minus 2 divided by x to the 5th minus 4x cubed plus 1. Gentlemen, you need to stop talking, because you will get very confused if you don't understand this lecture. So pay attention. So the highest exponent for the numerator is a 2. And the highest exponent for the denominator is a 5. That's why I'm dividing the leading term, which is x squared, and x to the 5th. When you divide, that means you simplify. Yes? You're going to get 1 over x to the 3rd. Now, if you don't know why that is the case, this is why. X squared is x times x. X to the 5th, that means you have to multiply x 5 times. X divided by x is 1. X divided by x is 1. Since everything's simplified, there's nothing on top, you're going to put a 1. That's x times x times x. That 1x to the 3rd. Everybody okay? So that's how I got that. Now, understand that x is a large number. Well, if you have a large number to the 3rd power, it's going to be a large number. Are we okay? 1 compared to a large number is a very, very small number. So if you take a small number and you're divided by a large number, you're going to get 0. The value is approaching 0. Is that good? For example, if I have $1, yeah, there are 1,300 students at this school, roughly. Yes? If I take $1 and I have to divide that evenly for 1,300 students, then each student will get 0. Not even a cent. You guys see that? So if you take a small divided by a large value, just know that the answer is going to be close to, very close to 0. Is that good? It's not 0, but it's very, very close to 0. So keep that in mind. If you take a small value and you divide it by a large value, okay, eventually that number is approaching 0. That's what we mean, is approaching 0. It's not 0, it's getting close to 0. So in this case, our horizontal asymptote is 0. Now, what does that mean, Ms. Tran? It means that if you take the limit as x approach infinity of the function m of x, the function is approaching 0. That's what that means. Okay? Same thing on the other end. This means the limits as x approach negative infinity, yeah, of m of x, the answer is going to be 0 as well. Now, Ms. Tran, is there a situation where the right end limit and the left end limit doesn't go to the same number? There is. We'll talk about that later. Is that okay? But right now, we're going to cover like the easy case first. Okay? I'm going to graph this out so you can at least see why you have that situation. So this is the function that I just typed in. X squared minus 2 divided by x to the 5th minus 4x cubed plus 1. Okay? We're going to graph that. We're going to go to auto so we can see it. This is the graph. Now, it's very complicated, but we don't care about what happened in the middle. We care what happened in the end. Do you guys see that? And look at your end. As x get bigger and bigger, as x approach infinity, do you guys see that your function flat now and the y value is approaching 0? You guys see that? Same thing here. As x get more and more negative, that means your function go to negative infinity. Your function, look at your graph. Your graph flatten out and is approaching that 0 mark. You guys see that? Question. So that's what we mean here. Are there any questions so far? Yes or no? Okay. Now, let's talk about another case. We talk about when the exponents here are the same. We can cancel it out. We get a number. We talk about when the exponent of the numerator, which is the top, is less than the one on the bottom, then you're going to get 0 because you're going to have a situation of small divided by large. Do you guys see that? What happens if it's the other way around? What if the denominator is bigger than what if the numerator degree is bigger than the denominator degree? Yeah? Then we have a situation. Is that okay? We will not have a horizontal asymptote. Is that good? This is a situation where your end behavior is going to go to infinity. Are we okay? Where it goes, we'll talk about that in a moment. Is that good? But when you have this situation, you're going to go, no, it's going to go to either positive or negative infinity. Are we good? But there's one special one. And this special one is when you have the degree or the exponents of the numerator is greater than the one in the denominator by 1 only, by 1. So if the top is 5, the bottom is 4. Or if the top is 3, the bottom is 2. The exponents differ by 1. Is that good? If you have that, you have an asymptote, but it's called a slant asymptote. Okay? And that's what we're going to cover right now. So this is the next case, case 2. You're going to have a slant asymptote. And it tells you this. If you divide the quotient of the rational function and you get a linear expression, a linear means it have to be in this form. Ax plus b. Keyword is have to be x. Okay? This x is to the power or the exponent of 1. That's what I'm talking about here. When you divide x cubed and x squared, you're going to get x. When you divide x to the 5th with x to the 4th, you're going to get x. This is an exponent of 1. You guys see that? So when you divide and you get a format of something with x, you're going to have a slant asymptote. What if it's x squared, not a slant asymptote? Is that good? If you divide and you get x squared, that's not a slant asymptote. So here's an example. This is an example where you have a slant asymptote. My leading term is x cubed, because that's the term with the highest exponent. The other term is x squared. When you take x cubed and you divide it by x squared, when I take x cubed and I divide it by x squared, do you guys see that I have x'd? That is linear. Okay? Therefore, you're going to get a slant asymptote. Now, I happen to divide this out for you. When I divide, this is what I got. X plus 3 plus a remainder. This is my remainder. My slant asymptote is just the x plus 3. We don't care about the remainder. Okay? Let's do this part by part, because there's two key important things here. The first one is, Ms. Tran, how do you get that? And the second thing is, what's the end behavior, Ms. Tran? So there's two things. What's the limit as x approach infinity of f of x? And then what is the limit as x approach negative infinity of f of x? Okay? So the first thing, Ms. Tran, how do you get that? Number two, Ms. Tran, how do you find the limit as x approach positive or negative infinity? So we're going to talk about the first one first. And this will help. You got to make sure you know this one from Math 3. You're going to have to use long division. Okay? If you don't know long division, that's why I create one for you here to help you remember. Are we good? Yes? All right, here we go. When I draw this on the Microsoft Word, it's kind of funny. So I need you to connect this for me so that it looks like a division. There you go. Okay, so it's division. Okay? All right. This is what you do. I'm going to cover this up. You want to find a term so that when you multiply to this x squared, you're going to get x cubed. Everybody okay? So the term is x'd. Are we good? Pay attention, because this is going to be confusing, some of it. So, as x. Now I'm going to take this x, and I'm going to multiply to both of these terms. So x times x squared is x cubed. Are you guys okay with that? And then x times negative 2, there's the negative 2x. Are you all right? Yes? Now, I don't have x squared, as you can see. You guys see that? So that's why I leave this blank. The next thing you're going to do in long division is that you have to subtract both of these terms to the polynomial on top. Is that okay? But here's the problem. Most of you, when you write this minus, you only subtract the first term. You don't subtract the second term. Is that all right? You get confused on that sense. So this is what I will teach you now. Instead of subtract, imagine it's a negative in front of both of these terms. Distribute that negative in. So whatever you have here, negate that sign. That means you have distribute in the negative. Once you distribute in the negative, you're going to add them for me. So this is what you do. You're going to put whatever that sign is, do the opposite. So that's a plus, you're going to put a negative. If that's a minus, you're going to change that to a plus. This is you distributing that negative in to both terms. Once you distribute, it's no longer a subtraction problem, but it's become an addition problem. Okay? And this will cancel out. Make sure it cancels out. And then a negative x plus 2x is going to be a positive 1x. That's where this x comes from. You guys see that? And then I take this term, which I didn't touch, I bring that down. Okay? And then I also bring this one down. You will see why in a moment. Okay? And then I wrote this one wrong. you're gonna have to cross this out and then put a 6 right here, a -6 here. But we'll get there. So the next thing I have to do is I want to find a term that when I multiply with x squared, I get 3x squared. So that term is a +3. You want exactly the same thing as this. So 3 times 2x times x squared, is 3x squared. 3 times -2 is a -6. So you're going to have to put that right under the number. Okay, not the x. I'll fix that later on my notes. So now, one more time. Yes, you want to subtract, but instead of subtract, you're going to distribute that negative in, and then you add for me. So whatever that term is, do the opposite. So that's a negative. Whatever that term is, do the opposite. So that's going to be a plus. So now you're going to be adding these instead of subtract. Okay? Do you understand what I'm doing? Or do I need to show you in a different way? You okay? All right. If you need to, then you can ask me later. That cancel out. I didn't do anything with the x, so it's going to go down there. But I have a -4 plus 6, so that's going to be a 2. What I'm saying is I don't care about this one. Okay? Once you get to this number, you're done. This is your slant asymptote. Okay? Do I need you to get here? I don't need you to get here. Is that all right? So what you need to do is that once you find that number, you can stop working altogether. You can stop your division. Is that good? I need that. How are we doing? Are we okay? If you need help, you ask. But you're going to see more of this, so we're going to go over it. Now, that's answer why or how I got the x plus 3. The next thing we're going to talk about is, Ms. Tran, what the heck does this mean, and where's your functions going to go? Well, here's what it means. If you guys know how to graph this line, right? Yes? This means this is your y-intercept. So that means on the x-axis, on the y-axis, you're going to go to 3 right there. Okay? The slope here is 1. So that means to get to the next point, you're going to go up 1 over 1, up 1 over 1. So this is your line. You guys see that? This is your slant asymptote. Now, the cool thing is, whatever the end behavior for that line, that's going to be the end behavior for your rational function. So if this line, if you notice, is a line that is increasing. So that means as x approach infinity for this line is going to infinity because the function is increasing. Do you guys see that? Yes? That means your function, your rational function, is going to do the same thing. It's going to approach infinity. So whatever the end behavior for that line, your rational function is going to behave the same way. That's why we got to know when we divide. Is that good? So if you look at on this left end right here, that means the limit as x approach negative infinity. So as x go to the negative side, your function, look at the line. The line x plus 3 is going down. That means your function is going to go down too. It's going to approach negative infinity as well. So whatever your division is, whatever your answer is once you divide, that line or whatever result that is going to have that same behavior as your rational function. So going back here, as x approach infinity, your function, because it has a slant asymptote of a line, which is increasing, as x go positive, the function is going to go positive infinity. As x approach negative infinity, your function is also going to go to negative infinity. How are we doing?
Good.
Are we good? But here's the cool thing. Okay? If this worked for slant asymptotes, it's going to be true for other things as well. So now we're going to talk about a situation when we divide and we don't get a linear quotient. So we talk about this. If I have x to the fifth and I divide it by x squared, yes, what I'm going to get is x to the third. Are you guys okay? Yes? So now, this is what we say. The end behavior of this polynomial, is going to be the same as the end behavior of this one. Is that good? While we cannot graph this, we don't know what it looked like, but we know the end behavior of something similar to it. Are you guys good? This one, you guys know how to graph this one? It's cubic. So x cubed looked like this. Is that good? So what we're saying is that the end behavior of this is going to have that same format. Is that okay? We might not know what happened in between, but we know the ending will resemble this one. Is that good? Now, Ms. Tran, what if it's a different exponent? What if this is a 4, Ms. Tran? Then you're going to have x squared. Yes? You know what x squared look like, right? X squared is a parabola. It's look like this. It's a positive x squared, so the parabola will open up. You guys see that? So what this means is, while I don't know how to graph this one, I know the end is going to be the same as this one. So your end behavior is going to look like this. We don't know what happened in between, but the end is going to resemble that one. Are we all right? Yeah? Now, Ms. Tran, what if I have this one and I have a negative? Well, when you divide, you're going to get a negative x to the fourth. Are you guys good? Yes? Now, what happened with, what does x to the fourth look like? Well, you got to know that this is an even degree function. Yes? Even degree means either both ends go up or both ends go down. Are you guys good? Because it's a negative leading terms, both ends gonna go down. So I don't know what this look like, but I know both ends of that function is gonna go down. And because this because the end behavior of this is gonna resemble that one, I know the end behavior of this rational function is gonna be doing this at the end. Does that make sense? Yes? So what you need to do is you gotta divide. It's like you simplify it. Make sense? Once you simplify it, then it's gonna get into something that you know. Are we good? That's why we're doing this. Are we all right? Any questions on this one? Is this good?
Yeah.
All right. So what's the key idea, Ms. Tran? The key idea is this. If the degree is the same, you're gonna get a horizontal asymptote. If the degree on top is smaller than the one on the bottom, you're going to get a 0 horizontal asymptote. If the degree on top is bigger than the degree on the bottom by 1, you're going to get a slant asymptote because you're going to get a line. Okay? But anything else where the degree on top is greater than the degree on the bottom, not by 1, then you're going to have to simplify and see where the end behavior of the simplified function goes to. That's going to be your end behavior of the rational function. Are we good? So I put a little note here because the slant asymptote is something that is important. The degree of the numerator is exactly 1 greater than the degree of the denominator. So make sure that is clear. That's the only time that you're going to get slant asymptote. Okay? So highlight that for me. The textbook, they call it the slant asymptote, but in some textbook, they call it oblique asymptote. Okay? Don't ask me why, but that's what it is. How are we doing? We're good? Okay. So we're going to take a look at one of them. One. We're going to start on it because that's all we have time for. It says, given this function, determine the end behavior using limit notation. Okay? Now we're going to test first. We're going to look at the leading term. In this case, the leading term on top is x squared. On the bottom, my denominator is x. When I divide x squared with x, you guys agree with me? I'll have x. Yes? X squared, x times x, and then divided by x, then one of the x cancel out. Because you have x, which is a degree of 1, that's linear, you're going to have a slant asymptote. This tells you you're going to have a slant asymptote. Okay? So now you're going to divide. Is that good? Yeah? We're going to divide. So I want you to show you how to do this one more time. You have x squared minus x. Ooh, careful. This is inside. And then the outside is what you're going to divide. That's x plus 1. Okay. Only look at the first term. I want something that when I times x, I'll get x squared. So that's going to be x. X times x is x squared. Everybody okay? So we're going to write that. X times x, that's x squared. X times 1, that's a positive 1x. So that's a plus x. How you doing? Okay, now watch. Remember, we have to subtract both terms. So instead of subtract both, I'm going to distribute the negative into both. So I'm going to negate both of these signs. That's a plus, now it's become a minus. This is a plus, now it's become a minus as well. And then I'm going to add. Okay? So this is what I'll get. X squared plus a negative x squared cancel. The first term got to cancel. A negative x add another negative x is a negative 2x. Are we okay? Now, I want to know, I don't have anything to pull down, so I'm going to keep on dividing. I want to know a term that when I multiply with x, I'll get negative 2x. That's going to be negative 2. Yes? Because a negative 2 times x is a negative 2x. A negative 2 times 1 is a negative 2. But I'm going to stop there because I got my number already. You guys see that? When you find that constant, that number, you're done. That's your slant asymptote. Is that okay? So my slant asymptote is x minus 2. That's my slant asymptote. Y equals x minus 2. How are we doing? We okay? Now, what does x minus 2 look like? Well, it's a line with a positive slope. So the line is going to look like this. Are you guys okay? I don't need to graph them. I just need to make a sketch. And this is what I know. I know that as x go to the right, you guys see the function is going up? Yes? So this tells me the limit as x approach infinity of the function f of x, which is this function, it will have that same end behavior, which is infinity. That's the end behavior that this thing is going to have. And as for the left end, this is the limit as x approach negative infinity. Notice for this slant asymptote, bless you, the function is decreasing. That means your function, your rational function, share that same end behavior. And that's your answer. Okay? We don't need to graph this. We only need to know the slant asymptote to determine the end behavior of your rational function. I graphed this out on decimals for you, so you can see there's my slant asymptote. Do you guys see that? Look at the function on the left. This is the function on the left. It does resemble the end behavior of the line. Look at the one on the right there. It does resemble, see, the asymptote or the line on the right. You guys see that? Yes? So wherever that slant asymptote go, your function is going to go with it. That's what this means. Any question? We're going to stop there. Let's clean up. Go. Now, homework. Make sure you know when it's due. I will have tutoring tomorrow and Wednesday. If you need extension or the one that is not due yet, then you come so I can help you out. Okay? All right, let's get your phone, please. I need to update this one, your attendance. So give me a moment.